Okay, so getting back to this example, we're finding a basis for this set. We've put our vectors into the columns. We've row reduced it. Now I'm going to circle the pivots here. So based on those pivots, how are we going to get our basis? The third, and this goes to show you can't just cancel off whichever ones you want, right? We have to cancel off the third and fifth vectors. That's because this is the third column and the fifth column, right? Those are the two we have to get rid of. Because imagine if we didn't have these two polynomials, then when we had put this matrix together, we wouldn't have had these two columns, which would have meant when we got over to here, we wouldn't have had any free variables left, right? So that's the reason you want to get rid of those two polynomials specifically. Yeah, never mind, I figured it out. Okay, is everybody okay with that? So the basis would be these three polynomials, and again, please write them down as polynomials. Don't write them as vectors in R4 or anything like that. Okay, so just make sure that your answers are making sense, right? If I ask you for, a set of polynomials, make sure you give me polynomials. By the way, the basis would not be the span of those three. Sometimes people overuse. I see people throw the word span around like it's nothing. The basis is not the span. The span is the whole space S. The basis is just this list here. It's just this list of vectors. Okay. It's kind of like another example is if you had like the null space of A. I'm just going to make this up really quickly. Let's say your null space of A turned out to be 2r minus s, and then r minus s minus t, and then 2s plus 3t or something like that. Let's just say this was the null space of a matrix. Okay. Then what I'll sometimes see people do is they'll bust out the variables and they'll come up with the null space equals 2, 1, 0, comma, -1, -1, 2, comma, 0, -1, 3. So you bust out the r, the s, and the t, and you get these three vectors, right? But what you would want to say here, you wouldn't want to say that that equals the null space. What you would want to say is a basis for the null space of A. So the words basis are important there. If you just write null space equals that, then it looks like you're saying, oh, the null space has three vectors in it. But actually, you don't mean that at all. The null space has a whole infinite family of three-dimensional vector space for the vectors in it. So just be a little careful. I mean, I'm not going to like take off all the points on you if you write it slightly wrong, but I might take off one point if it doesn't make sense to me here or there, and that can add up a little bit. Yeah, Christian?
So that is different from finding the basis for S, the basis for the null space?
Yeah, I was just making up something over here. It's just like, I just happened to remember this from the recent homework assignment where it asked you to find a basis for the null space, row space, and column space of these various matrices. And some people were being a little sloppy about not writing basis for on things. They were just writing null space equals this, when really it doesn't. It equals that. So there's a difference there. There's a difference between a set of vectors that's like a basis for something versus the whole space of vectors that you're talking about. And it's just good to make sure that you're communicating that in the right way.
So how do we write it again for finding basis?
Find a base, you just, right here, you just list the first, you would just list these three polynomials that are left, right? 1 minus 2x plus 3x cubed, and then this one, and without the word span in front of it. No, don't write span in front of this. Okay, and then the third one would be this one over here, 2 minus x plus 4x squared minus 7x cubed. It would just be that. Okay, does that make sense? Okay. Well, I've really covered pretty thoroughly everything in the first 9 sections of chapter 4. I haven't done so much on the inner product spaces or the linear transformations. I think that's what we should spend the rest of the time on, unless there are further questions on anything that we talked about so far. So far, so good? Okay. So in terms of, let's see, I'm trying to decide. Would you guys like me to talk about linear transformations next, or do you want me to do some examples on the Gram-Schmidt process next? What do you guys think? Because I don't have either of those. Well, I have some linear transformation stuff on this, on the review packet, or on the review session questions. But do you guys have a preference what I go over in the next little bit here? You want to see about linear transformations, or do you have questions on the homework for tomorrow? That'd be another thing I could ask about if people have issues with the Gram-Schmidt problems in 4.12. What'd you say, Frank?
I'll do Gram-Schmidt.
Okay. Do you have a question, Christian?
Yeah, just doing the homework for tomorrow.
Yeah.
As well, like number 26, I had a question.
Number 26. Okay. Shall we just do it? Some of you maybe haven't done it yet, so this will be just, I'll just help you with that. We'll just use that as another practice problem. So I think I'm up to number 4. I haven't been doing very many problems, but I've been talking about a lot of parts with a lot of follow-ups, so it's okay. All right, so basically the vector space on this example, this is from the homework, is the 2x2 matrices over the real numbers. And they give you an inner product. Maybe this is what your problem was, Christian. Did you see where the inner product was given? 3 lines above the question. It's 5 times A11 B11 plus 2 times A12 B12 plus 3 times A21 B21 and then plus 5 times A22 B22. So that is a weird looking expression, but that turns out that is an inner product. Okay? Technically, and I could ask you to check an axiom, 1 or 2 of the axioms, but let's move on to the actual question here. It just says find an orthogonal basis. Find an orthogonal basis for, I'll call it S, which is the span of the set of 1, -1, 2, 1, and the second vector I'm going to use is 2, -3, 4, 1. Okay. Notice, first of all, that they're only asking for an orthogonal basis. They're not asking for an orthonormal basis. So we don't have to normalize anything. We just have to orthogonalize these vectors. Okay? So that's where Gram-Schmidt comes in, right? The Gram-Schmidt process. So here, these are my 2 vectors. I'm going to call them V1 and V2. Okay? And I'm going to just go through the Gram-Schmidt process. Remember, I'm going to give you the formulas, so you don't have to worry about it. W1, you probably remember the formula. It's just equal to V1. Okay, so W1 turns out just to be 1, -1, 2, and 1. Okay? Again, so this is problem number 26 in section 4.12 from the homework assignment. And then W2, just remind you the formula. It's V2 minus the fraction where you have the inner product of V2 with W1, okay, divided by the norm of W1 squared times W1. Okay, so we need to work these things out. So V2 is the second vector, that's 2, -3, 4, and 1. And I'm going to subtract from that this expression here, which I'll fill in a second, times W1, which was 1, -1, 2, and 1. So this is the Gram-Schmidt process. Oh, let's remember what we have to put here. On top, we have to put the inner product of these 2 vectors. So here are the 2 vectors. They're actually sitting side by side, and here's the formula. So I'm going to take 5 times A11 times B11. So that's 5 times 1 times 2, that's 10. 10. And then plus 2 times A12, B12, so that's 2 times 3, right? So that's 6, good. And then the lower left corner, 3 times the product of these two is 24. And then 5 times the lower right corner, which is 1 times 1, that gives me 5. Okay, great. So you add all of that up and you get 45, right? Okay, great. So we put 45 right here. Put 45 right there. Very simple. Okay? And now on the bottom, I have the norm of W1 squared. That is just the inner product of, so the norm of any vector squared is just the inner product of that vector with itself, right? With itself. Okay, so for that, I'm going to take W1 inner product with itself. That's the first vector with itself. So 5 times 1 times 1 plus 2 times -1 times -1. Okay, I have to write this down. Can't do it in my head. So 5 times 1 times 1 is 5. 2 times -1 times -1, that's 2. 3 times 2 times 2 is 12. And 5 times 1 times 1 is 5. So that comes out to 24? Okay, great. And there's a common factor of 3 inside of there, so this becomes 15 over 8 if I do that. And now I just have to subtract, okay? We just have to subtract, so 2 is really the same as 16 over 8, and I'm subtracting 15 over 8 to get 1/8 in the first entry. And then I have -3, which is like -24/8, and I'm going to add 1/8 to that. So that would be -23/8. And then in the lower left corner, I have 4 minus 38. So this is really 32 over 8 minus 30 over 8, which is 2 over 8, or in other words, 1/4. This is another one of these things, you know, if you make a little mistake and get a number wrong, I'm not going to crucify you for it. It's just easy to have that happen. And then the last entry, this is 8 over 8 minus 15 over 8, should be -7 over 8. Okay, so that's what you would end up with. So your final answer then would just be W1 and W2. That would be your basis. And that is an orthogonal basis. That's not an orthonormal basis, right? If I wanted an orthonormal basis, I would have to take each vector and divide by its norm. So for example, I would have to divide this vector by the square root of 24. Because the norm of W, remember we did the norm of W1 squared was 24. So I would have to divide this one by radical 24 if I wanted to normalize it. And then I would have to normalize this one too, which would be a pain. It would actually be quite a pain to figure this out because of the fractions. So we won't do it right now. But does that make some sense? Yeah. Okay. Great. Kristen, does that help you with your question?
Yeah.
Are there other people with questions on this Gram-Schmidt stuff? You said you'd give us the formulas for WW. Yeah, and I'll give you as many as whatever you would need. I might give you the W3 formula. I might ask you to do 3 vectors. I don't think I'd ask you more than 3, but I might ask you to do as many as 3 potentially. Okay, it's very computational, so it's not that bad. Oh, maybe I can give you a problem that is a little more conceptual. Let's try something. You guys are going to be so good on the group work tomorrow. So you're going to know everything that your group doesn't know because we're practicing a few examples now. Okay, so this is a more abstract example. Let's suppose that the norm of U is equal to 2. The norm of V is equal to 1. And the norm of W is equal to 6. And suppose that the inner product of U with V is equal to 3. I'm making this up right now. The inner product of U with W is -1. And the inner product of V with W, let's just say that is equal to 0. let's compute the inner product of 2u plus w with 3u plus v minus w. Okay. So you haven't seen one of these before. In the new book that we're writing, we have some more problems like this, because these are actually helpful exercises. Yeah, this one.
Normally, I thought U was the unit vector.
Oh, it can be. I'm just telling you here it's not.
Oh, okay.
U is just a notation.
Okay.
Yeah, usually we'd use U's for unit vectors. But here I just didn't do that. I just made this up right now, literally on the fly. The thing that's weird about this problem is I did not give you the vector space. I didn't tell you, am I working with polynomials? Am I working with traditional vectors? I didn't tell you anything about what the specific vectors are. But we can still answer this question because we have properties of the inner product, those 4 axioms. Remember, right, the 4 axioms that define an inner product. We can apply those here, right? Let's think about what those axioms told us. Those axioms tell us things like, oh, I can factor out constants, right? And when I have plus signs, I can distribute into 2 separate terms, right? So I can actually, the solution, the way you do a problem like this, guys, is you just go back and you sort of do a good old-fashioned FOIL that you would have done to solve problems like this in high school. So this inner product, I'm just going to jump down here with an equal sign to save writing it again. What I can do is I can say, well, I'm going to take the inner product of 2u with 3u plus v minus w and add it to the inner product of w with 3u plus v minus w. I can do that. That's partially foiling it out. And then I can continue to FOIL it out by foiling in the second. Now, technically, the axioms don't allow me to FOIL plus signs in the second slot. But remember that you can switch the first and second slots around and then do the factoring and then switch them back. So I may as well just go ahead and do that. So this is just going to be the inner product of 2u with 3u plus the inner product of 2u with v minus the inner product of 2u with w. I'm going to need some more room here, aren't I? Then I have to do the second part of this. So then it's going to be plus the inner product of w with 3u, and then plus the inner product of w with v, and then minus the inner product of w with itself. Okay, so first thing I need to do is pause and let you guys write that down and make sure that you are happy with it. And this problem doesn't have anything to do with Gram-Schmidt. This is just simply the axioms of an inner product, okay? Everybody comfortable? We sort of had 2 terms and 3 terms, so we FOILed it out. We end up with 6 things here, right? We have 6 things. Everybody with me? Everybody good so far? Now the constants, the 2's and the 3's, those constants, they can be pulled out, remember? One of my axioms of an inner product allows me to pull that out. So that's going to become a 6. And then, by the way, the inner product of u with u is another way of writing. Can I rewrite that using the norm? How would it be rewritten using the norm?
The norm of u squared.
Right, it's the norm of u squared. Okay, so the first term is just 6 times the norm of u squared. Okay? The second term has a 2 in front of it. I can take the 2 out. It leaves me with the inner product of u with v. Okay? Then the next term also has a 2. I have a minus 2 times the inner product of u with w. Then I have a factor on the next term. I have a factor at 3. So I can pull that out. 3 times the inner product of w with u. And then I have plus the inner product of w with v. I don't have to change that one. And then the last one, what is the inner product of W with itself? How can I rewrite that? The norm of W squared, right? Are you guys starting to see how we do this problem? How we're going to do it? Yeah, see, we've split it all down into like simple terms, and now we have all of our given values up here. Right? Everything that I gave you up here, we can now start using all that stuff. Okay, so let's just start plugging it all in. The norm of U squared would be 4, right? So 6 times 4, plus 2 times the inner product of U and V was 3, so 2 times 3, minus 2 times the inner product of U with W, which was -1. Oh, the inner product of W with U, I don't see that up there anywhere. It's the same. The inner product of W with U is the same as the inner product of U with W, so I can just use that. It's -1. Okay, very good. What's the inner product of W with V going to be? That one is 0, okay? And then the last one is minus the inner product of, the norm squared of W, which would be 6 squared, which is 36. Okay, so we get 24 plus 6 plus 2 minus 3 minus 36, whatever this comes out to. 32, looks like negative 7 or something like that? Negative 7? Okay, great. Negative 7. Sounds good. Make sense? Okay, so this is we didn't have any homework problems like this, but it's a nice problem. I should have given you a homework problem like that. It's a nice practice problem. And you are going to see this. I'm going to give you one of these in the group work tomorrow too, so you'll know how to do it already. Okay. Let's see, what else? So we've kind of practiced the Gram-Schmidt a little bit. We still have some more homework to get done with on that. Just trying to think what else we should go over. The angle between two vectors. That's pretty easy. Does everybody know that formula? Just make sure you know, the cosine of an angle between two vectors, V and W. This one shouldn't be too hard for you because it's the same formula that you used in Math 250B, right? So that keeps it pretty simple. So you have to know that one. And then just, I guess the only other thing is just making sure you can check the axioms of an inner product. You want to make sure that you know how to check those axioms. Maybe let me give you a quick, and yeah, anybody who needs to go, of course, is fine. I said I'd stop at 8, but I'm still talking, so I'll keep talking, and at some point I'll stop talking. But just I just want to make sure that I don't omit something that is worth reviewing. I think I did a very thorough job on the first 2/3 of chapter 4, but just this very last part. What if I asked you this? Is the inner product of f of g equal to the integral from -1 to 0 of t, f of t, g of t, dt, a valid inner product on c of -1, 0? This would be a nice question. I think this is number 5. Could be off on my memory. Oh, it's 6? Sorry, number 6. Okay. Number 6. Is that a valid inner product? So, it's just, I'm asking this in part just to remind you of the axioms again. So just, it's worth putting these on flashcards and laying them under your pillow at night for the next 3 nights. Absorb it by osmosis or something. Right, the inner product of a vector with itself, what do we know? The axiom A, what has to be true about that? At least 0, and when can it equal 0?
When they're both 0.
Only when the vector itself is 0, right? So that's the first axiom. You don't need to, you guys already have this in your notes. These are just the regular, same axiom. Just writing them down again. Let's see, what else do we have? The inner product of v with w can be rewritten as how?
W would be
Put the w first, exactly. The inner product of w with v, very good. What's the next one say?
K times V.
If I have a constant times a vector, so k times v, inner product with w, what can I do?
Pull
Pull it out.
Good, and I can even do that with the second slot, because if there's a k in the second slot, I can switch it, pull it out, and then switch it back, right? And then the last one is the one if I have like v1 plus v2, inner product with w, and that's the inner product of v1 with w, plus the inner product of v2 with w. We were using all of these on that previous problem that we just did, right? When we foiled that thing out on the last problem, we were basically using part C and D, and we even used part B because in some cases the vectors were in the opposite order to how they were given. So yeah, so those are your axioms, and now that I've written them all down and winded myself talking these through, has anybody in the meantime had any thoughts about whether this would be a valid inner product or not? Well, if it goes wrong, did I ever say something in class about when this thing fails? Well, look at axiom B, for example. Axiom B. If I switch where the f and the g go, is that going to change what the integral is? No. So axiom B, I mean, this one's easy, right? If I have a constant in front of the f, so k times f, so if I put a k here, right, will I be able to pull it out?
Yeah.
Sure. It's an integral. Constants can be factored in and out of integrations. No problem at all, right? No problem there. What if I had like an f1 plus f2? So I had two functions added together here. Would I be able to, inside the integram, kind of split it into two, distribute it into two terms, and then have two integrals? Mm-hmm. Absolutely. So this is, I think, what I said in class before, guys, is that usually B, C, and D go smoothly. They are mainly algebraic properties that, unless I give you something really extremely crazy, they should work just fine. There should not be any issues there. It's usually the first one that doesn't work. So that's my question, does the first axiom work? Because that's really what it's boiling down to now. What is this expression? You know, if I do this inner product, I'm getting. No, by the way, the one that we did in class didn't have the t in it. In class, we've already done the one where we said if you just integrate f of t times g of t, then that's an inner product. That was a valid inner product. So the real issue here is I threw this t in here. Does that mess it up? So let's just see. So we put this in, we get an integral from -1 to 0 of t times f of t squared dt. And the question we have to ask ourselves right now is, will this come out to a positive number? Anybody have thoughts on that? Pam?
Will we always be given the integral?
Yeah, I have to give this to you. This has to be given. Yeah, that's definitely true. Is that going to be greater than or equal to 0? Why not, Louise? If the t weren't here, if the t wasn't there, then would this be greater than or equal to 0?
Yeah.
Then you have a positive function. When you square something, it's positive, right? And you're doing an integral of a positive function, so of course it would be positive. So the question is, does it mess things up when I put the t in front of it there? I think so. Yeah, because look at your interval of integration. Look where t is going between. You're plugging in values of t. This is dt, right? dt. T goes from -1 to 0. And that's a problem.